moment of inertia, radius of gyration. And also we discussed the theorems of moment of inertia also. Today we are going to be discuss the moment of inertia of the different rigid bodies and also different system of particles. For example, there are the two particles of masses m1 and em2 separated by a distance small r. Say these two particles are going to be rotate about a axis passing through the center of mass perpendicular to the line joining the two particles. That means like this. This is the axis of rotation. Now we require to find out the moment of inertia of these two particles. As this is center of mass, let the distance of the first particle m1 from the center of mass is r1 and distance of the second particle m2 from the center of mass is r2. We already studied that if the distance between the two particles is small r, then the distance of the center of mass from the first particle r1 is equal to, we can write as m2r by m1 plus m2, and r2 is equal to, we can write as m1r by m1 plus m2. When you know the distances, perpendicular distances, then easily we can write the moment of inertia of these two particles. How to write? Yesterday we already discussed that the moment of inertia of a particle which is following the circular path or which is going to be rotate about a axis. So to know the moment of inertia, what we require to know? Number one, mass of the particle, small m, and the perpendicular distance of the particle from the axis of the rotation, say that is equal to small r. So we can write I is equal to mr square. Now basing on this concept, we are going to be find out the moment of inertia of these two system of particles. Moment of inertia I is equal to, here we have to write the moment of inertia of the first particle and also moment of inertia of the second particle. That is I1 plus I2. I1, mass of the first particle is m1 and its distance is r1, perpendicular distance, do remember, r1 square, plus I2, that is equal to m2 into r2 square. Now substitute the distances r1 and also r2. r1 square, m2r by m1 plus m2 whole square plus m2 into r2 means m1r by m1 plus m2 whole square. From this, I is equal to, we can write m1 m2 square r square by m1 plus m2 whole square plus m2 m1 square r square by m1 plus m2 whole square. I is equal to, now what we can take common here? We can take m1 m2 r square also, m1 plus m2 whole square also. Then what you get? m1 m2 r square by m1 plus m2 whole square. Then what will be left here? Here m2 will be left plus here m1 will be left. 1 m1 plus m2 and 1 m1 plus m2 will be gets cancelled. Finally, the moment of inertia of these two system of particles about that axis you will get as I is equal to m1 m2 by m1 plus m2 into r square. You better to remember the value of this one also. This is actually called as the reduced mass. That is, I is equal to, simply we can write mu r square. So this is the moment of inertia of those system of particles. Now we can go through the next example. Moment of inertia of a ring, let us find out. This is a ring, mass is equal to capital M and radius is equal to capital R. First of all, we require to find out the moment of inertia of this ring about its own axis. One axis is nothing but which is passing through the center and perpendicular to its plane. How to find out? Consider a small element of mass dm, say length is equal to, for example, dx. Now the distance of this element from the axis of the rotation, perpendicular distance, is equal to how much you get? Capital R. Then the moment of inertia of that element, already we know how to write that one. Di is equal to nothing but dm into r square. Then what is the moment of inertia of the whole ring about that axis? That is, I is equal to, we can write integration of dm into r square. Then how to write the dm? Dm is nothing but, you see, mass is distributed along the circumference of the ring. So mass is distributed along the circumference, that is equal to 2 pi r. Then for dx length, how much mass will be distributed? Say that is equal to dm. Dm is equal to, we can write as m by 2 pi r into, what you can write? Dx. Substitute that one. Now moment of inertia I is equal to, you will get integration of m by 2 pi r into dx and also r square. And what will becomes outside? M by 2 pi r into r square integration of the dx. Dx is a small element that I assumed here. Now if I integrate this small element, that is the length of this small element throughout the circumference of this ring, this length is, total length will be, simply will become again 2 pi r. Then 2 pi r will be gets cancelled. Then simply you will get moment of inertia of the ring about the axis passing through the center and normal to its plane is equal to, I is equal to mr square. Directly also we can understand that the water may be mass is there that is distributed at a equal distance from the axis of the rotation. So simply we can write directly I is equal to the mass m into r square. Total mass which is distributed along the circumference into r square. But because here mass independent of the position of that element from the axis of the rotation. So this is the moment of inertia of the ring about this axis. Now we can easily find out the moment of inertia of the ring about the diameter and whatever may be axis is given. By applying the either parallel axis theorem or perpendicular axis theorem, easily we can find out. So let us go through the one or two examples to find out the moment of inertia of the ring. Let us find out the moment of inertia of the ring about the diameter. This is the capital R, mass is equal to capital M. I am going to be find out about the diameter. Now, by making use of the perpendicular axis theorem, easily we can find out the moment of inertia of the ring about that axis of rotation, that is about the diameter. You see how? Now this is the one axis that is about the diameter. Let me call that is equal to x axis, or you can say y axis. Let me choose one more axis, perpendicular axis in the plane of this ring, say that is the x axis. And of course, as this is the diameter, this is also diameter. That means whatever may be moment of inertia you will get about this axis. Same moment of inertia you will get about this axis also. That is here simply we can write Ix is equal to what? Iy. But we require to find out the Ix value or Iy value, with both are actually equal. But already we discussed that the moment of inertia of the ring about the axis passing through the center and normal to the plane, like this. This already we discussed, that value is equal to, say this axis is equal to Iz, Iz is equal to, already we discussed that is equal to how much? Mr square. Then how to find out Ix and Iy? Now you see these two axes are became to perpendicular axis in its plane, and the third axis z axis which became normal to the plane of this ring passing through the point of intersection of these two perpendicular axes in its plane. So now directly we can apply the perpendicular axis theorem. Ix plus Iy is equal to nothing but Iz. But you know these two are same. Why? Because both are the axis, both symmetrical axis, nothing but both are the axis which are passing through the what? A diameter of the ring, like that. So both are same. Let me call that is I plus I. That is equal to already you know mr square. So 2I is equal to, you will get mr square, that is I is equal to, you will get mr square by 2. This is the moment of inertia of the ring about the diameter. So when you know about the diameter, and of course we can find out the about the tangent also. And of course here the tangent is parallel to the plane, or you can say in the plane of the ring. Then how to find out the moment of inertia of the same ring about that axis? Now here we will make use of the parallel axis theorem. We already studied that the moment of inertia of the body about the center of mass. Here presently this axis is nothing but diameter axis. So that already we got how much? ICM is equal to is nothing but mr square by 2. Then how to find out about that parallel axis? And the distance between these two axes, parallel axis, say that is equal to how much? Capital R. Now if I is the moment of inertia about that axis, I is equal to, we can write Ig plus mr square. Ig, or you can say ICM, whatever it may be. Then what is the moment of inertia of this ring about the diameter? Already you would derived mr square by 2 plus m into r. R is the distance, perpendicular distance between the two parallel axes, that is equal to capital R. So mr square. Then this will become the 3 mr square by 2. Now see, here we are going to be find out the moment of inertia of the rigid bodies with respect to the different kind of the axis of the rotations. And if you are asked what is the radius of gyration about that axis of the rotation, that also easily we can find out. For example, in this problem, what is the moment of what is the radius of gyration of this ring about this axis of rotation if asked? Already we know that the moment of inertia of a rigid body simply can be written as I is equal to mk square, where m is equal to mass of the whole body and k is equal to radius of gyration. This is equal to, you see how much we got about this axis of rotation, means 3 mr square by 2. Mm will be gets cancelled. Then the radius of gyration about that axis of rotation is equal to, you will get under root of 3 by 2 into capital R. So in every example, whatever maybe we discussed till now, in that to find out the radius of gyration with respect to that axis of the rotation, simply the final found value will be equated to the mk square, and from that you can cancel the m values, and finally you can find out the radius of gyration also. And like this we can find out the moment of inertia of the ring about the diameter or about the some given axis, and etc like that. Let us find out the moment of inertia of the disc. Now this is the disk. The mass of the disk is capital M. Now the radius of the disk is equal to capital R. So with respect to what axis we are going to be find out? Simple. The axis is here passing through the center of mass and also perpendicular to the plane of the disk, like this. About this axis we are going to be find out. And the radius is equal to capital R. Then again we will go through the integration method. The moment of inertia of a small element we have to consider, and one thing it is very clear to us that the mass of the disk is distributed uniformly throughout the surface area. So I am also going to be take the one of those element circular element of radius small r and thickness is equal to dr and the mass of the ring is equal to here dm. Now whenever you write the moment of inertia of this element about this axis of rotation, then simply by integrating that equation we can find out the moment of inertia of the whole disk about this axis of the rotation. Then how to write the moment of inertia of this element about this axis of rotation? You see here the assumed element is in the form of a ring. So for a ring, the moment of inertia about a axis passing through the center and perpendicular to the plane of the ring, already we know how we wrote, that is di is equal to is nothing but dm into r square. Then what is the total moment of inertia of this disk? Simply I is equal to, we can write integration of dm into r square. Then how to write the mass of the element? If you write that one, then simply we can find out the moment of inertia of the disk about this axis of the rotation. You see here M is capital M is the total mass of the disk. It is distributed throughout the area. Area of the disk is equal to pi r square. But what is the area of this ring? Look carefully. When I stretch this ring, it will become like this. Now its length will become how much now? 2 pi r. And whose thickness I assumed is how much? dr. Then area will become how much means? 2 pi r into dr. For this area, how much mass you will get? dm. Then how to write the dm already you know? dm is equal to is nothing but mass per unit area, that is m by pi r square into area of the element 2 pi r into dr. In the next step, pi will be gets cancelled. Then you will get how much? 2m by r square into r into dr. When you substitute this value in that equation, we can find out the moment of inertia of the disk about the axis passing through the center and normal to its plane. That is I is equal to integration of dm. This is dm to m by, this is r square r dr into r square. Where to where the limit goes? Limit goes from the center to what? This. This element is stretched from this to here, that is 0 to capital R. So what will becomes common here? 2m by r square integration of r into r square, that is r cube dr, limits goes to 0 to capital R. Now I is equal to, you will get 2m by r square. Integration of r cube is equal to, already you know, r power 4 by 4, limits 0 to capital R, that is 2m by r square into r power 4 by 4, and finally you will get mr square by 2. This is the moment of inertia of the disk about an axis passing through the center and normal to the plane. I is equal to mr square by 2, and whenever you know this value, then happily you can find out the moment of inertia of the disk about the diameter also. You try yourself by applying the perpendicular axis theorem. That value is equal to, you will get mr square by 4, and with respect to the different axes also we can find out about a axis tangent to the disk, and of course this axis is present in the plane of the what? Disk. This also you try yourself by applying the parallel axis theorem, and you can find out about this axis also about the tangent. This axis is now normal to the plane of the disk. Then how to find out this moment of inertia? By applying the parallel axis theorem. Again you can find out, try yourself and get the difference between this situation and this situation. Here the axis is parallel to the what? Diameter, and here the axis is actually the normal to the plane of the disk. So like this we can find out the moment of inertia of the different rigid bodies. So here we discussed the different rigid bodies, moment of inertia of the different rigid bodies with respect to the different